Last time we ended on the topic of invertible matrices. We said that a matrix A, that's n by n, so a square matrix, we call that matrix invertible if there exists another matrix B that's also n by n, such that A times B is equal to B times A, and that's equal to the identity matrix. So where I is the n by n identity matrix. And an identity matrix, if you recall, that's a matrix with ones along the diagonal and zeros everywhere else. So notice that in this definition, I'm using square matrices. Something you could ask is it possible for a matrix that's not square to be invertible? And the answer is no, not really. So in the definition of an invertible matrix means that it has something called a right-sided inverse and a left-sided inverse. It's possible for a non-square matrix to have just a left-sided inverse or a right-sided inverse, but not both. Let me show you what I mean. So let's suppose A is an m by n matrix. If there exists a matrix B that is n by p, such that A times B, actually this should be an n by m, such that A times B is the identity matrix that's m by m, then B is called a right-sided inverse. It's like you have half of what you need. You found a matrix B where A times B gives you the identity. Now notice that I had put a P here, but if I multiply A with B, the n's would go away, and if I just had a P, I would have an m by P matrix, which is not an identity matrix because an identity matrix has to be square by definition. So in order for us to even get an identity matrix, it needs to be a square matrix. So that forces this one to be m, the same thing as the number of rows. So the number of rows in A have to equal to the number of columns. Now you can have a right-sided inverse. But notice if you multiply B with A here, you'll get a n by n matrix. And let's say it happened to be the identity matrix. Well, in order for these to be equal, because remember that the definition of an invertible matrix is A times B is equal to B times A. If we get the same thing, n would have to be n. So that would force this matrix to be square. So here we're saying this is not a square matrix. So you can't have a right-sided inverse and a left-sided inverse for a non-square matrix. So I'm just going to change a couple of things. Now we're not going to deal with right-sided inverses and left-sided inverses for non-square matrices. I just want to let you know that it's possible for these to exist. So let's say that we have an m by n matrix and there's another matrix B such that B times A is equal to the n by n identity matrix. Then B is called a left-sided inverse because B is on the left. So again, it is possible to have left-sided and right-sided inverses for a non-square matrix, but you can't be invertible. That only applies to just square matrices. Okay, let's move on. So the next thing I want to bring your attention to is that if you have an inverse of a matrix, a square matrix, then that inverse is unique. You're not going to have more than one inverse for a matrix. Now this doesn't say that every matrix has an inverse. In fact, that is not true. Not every matrix has an inverse. But let's say you do have an inverse. Then that inverse, there's only going to be one of them. And we're going to actually prove this. So here's the proof. We're going to prove this by contradiction. That means I'm going to assume that this statement is false. So we're going to assume that A has more than one inverse. So let's say we have B, that's n by n, and C, that's also n by n, are two inverses of A. So we have more than one inverse. Let's call them B and C. So if that's true, then A times B is equal to the identity. But since A times B is equal to the identity, we can multiply A times B by C. And that's going to be equal to C times the identity, right? If A times B is the identity, if I multiply this side by C, it's the same thing as multiplying this side by C because they're equal. Now, remember that matrices are associative. So what I can do here is I can put parentheses around these two. So I can multiply C and A first and then multiply it with B. And on this side I have C times the identity. Now remember, we wrote in the last video that the identity matrix times any matrix is that matrix again. So let's put that here. I'm just going to write it as recall that C times I is just C. So what I'm going to do now is I'm going to keep this here. And now C times A, well remember that C is an inverse of A. And since it is an inverse, that means C times A is going to be equal to the identity matrix. So we have the identity matrix times B is equal to C. And the identity matrix times any matrix is that matrix, so B is equal to C. So here we've just shown that if we assume there's more than one inverse, if there's two inverses, then this forces those two inverses to be equal. So now we have a contradiction. There only exists one inverse. Okay. So from now on, if I ask you to find an inverse of a matrix, you're only going to find one inverse because of this theorem here. And the last thing from this section I want to go over is that we denote the inverse of a matrix if an inverse exists. I think I have said this in the last video, but we're going to write it as a to the negative 1. Now something to note, a to the negative 1 does not equal 1 over a. We're never going to divide something, a number, by a matrix. That doesn't make any sense. We've never talked about doing things like that. So this is just how we denote the inverse. It does not equal 1 over that matrix.